So today I want to talk about three-dimensional data and their connection with deep learning. I suppose some of you knows much more about three-dimensional data because you are more experienced with that, but I want to talk just about uh, application of three-dimensional data for deep learning tasks and mostly about connection between them. So let's start from a general view where we can see three-dimensional data. So just a brief overview, we can see three-dimensional data when we work with robotics and when we have to navigate our autonomous agent or some robotic arm, for example, in our environment, and have to know when where we are locating in the space. In augmented reality, basically, we have to align our virtual three-dimensional world with the real world and make it attached as smooth as possible. When we talk about autonomous driving, obviously, when we have a car, we have to understand its environment in every moment of time and have to know about every object around our car to drive safely. And when we talk about medical image processing, usually it's better to work with three-dimensional data because the nature of data is volumetric, and therefore it's better to process medical image as three-dimensional data. So when we talk about traditional three-dimensional vision, it's based on physics. It's based on relations between multi-view images. When we have at least two points in space that are separated by some base, and therefore we observe our world from different points, and if we want to understand the scene in front of us, we just apply a lot of mathematics to this captured image from these points, and in this way try to reason relationships between these two images and build up some view of the scene in front of us. When we talk about three-dimensional learning, it's slightly different because it's based on knowledge. And in order to build the effective system for three-dimensional data, we have to develop a proper way to inject three-dimensional knowledge, to inject understanding inside the system. And potentially when we train our system or model properly, it will be able to see the same optical illusions as humans can see on such image. So let's talk about popular three-dimensional data representations. In one paper, I found such separation of popular representations. So basically, they are divided as Euclidean structured data and non-Euclidean data. When we talk about Euclidean data, it supposes that these data are within some grid structure that allow us to parameterize this data within some Euclidean space. And on the other hand, the non-Euclidean data not strictly belong to this space and can be described without it. So there no need to connect it to some space. And here we can see a few types of representations, such as descriptors, projections, RGB image plus depth, volumetric representations such as voxels and octaves, and multi-view representations. For non-Euclidean data, most popular ones are point clouds, meshes, and graphs. And one of representations not mentioned here is implicit representations. It is closely related to deep learning and became popular in recent 2 years. And it supposes description of three-dimensional space as some very complex function that actually is some trained model, but I'll talk about it a bit later. So let's take a look closer at some of these representations. Descriptors technically are more or less the same as descriptors for two-dimensional images, and basically are some handcrafted features that we try to calculate over three-dimensional data. And it can be calculated for object geometry, topology. Yeah, you can see my mouse pointer. So we can calculate descriptor of different properties of data, either shape, surface, or texture. Usually they are calculated to make further calculations easy. And in deep learning pipelines or machine learning pipelines, they are used as standard features. So we calculate them and then feed to some deep learning or machine learning model. As well, they can be local and global. Local for calculation over some limited part of space, some limited part of the object, and global for description of entire scene or entire three-dimensional objects. And as well, they can be intrinsic and extrinsic. Intrinsic suppose that they contain only local information that is not connected to the context of this particular part of space. On the other hand, the extrinsic suppose calculation of context information and space relationships to nearest regions. So in this way, we can simply divide them. Another type of representations are projections. They can be calculated, that can be transformed by projection into Cartesian, spherical, or cylindrical spaces. And usually two latter ones are used because they have more universal properties to work with such projections. And if we do such projections properly, they can be invariant to rotations around some principal axis, as in this example. One more representation, as I said, is RGB-D image. So that's some kind of mixed 2.5 dimensions, because it is still two-dimensional image, only single image, and we add some part of depth of one more dimension by injection of depth. and depth is still 2 dimensional. So in that way, it's 2.5 dimension informations. There are lots of data sets with such data, and most of them are interior scenes or some small objects. Why there are lots of data sets? Because such data became popular due to lots of cheap and available sensors that allow to capture such data. And there are a few known devices for these purposes. They are Microsoft Kinect system, Intel RealSense, and structure light sensor for iPad. And if someone of you still doesn't know, all of these sensors are available in our office. At least were available. So if everything will be okay, you can come back and try to play with such devices. Okay, let's proceed with further ones. So volumetric data, and the easiest one is voxel data. It has a straight connection to pixels in our two-dimensional image, but in this case we just add one more dimensions, the third one, and get voxels. There it's pretty straight, but quite not how to say, not easy, not so popular way of three-dimensional data description, because voxels are too heavy. They describe both occupied parts of space and non-occupied. They require lots of memory, and then they can describe tiny details and high-resolution data. So that's why these voxels are not very descriptive, and as you can see on the image below, the resolution in one dimension isn't too high. In this example, it is only 128 voxels. And one more type of volumetric data is octrees. Basically, octrees are just variable size voxels. And we can describe our object, our scene in 3 dimensions by different depths of details. And how it works, we divide each voxel by 8 parts. And we can do it multiple times. And in this way, we get such hierarchy of nested smaller octaves. And on this image, you can see example with 3 levels of details. When we have from 32 to 128 voxels one direction. And octree is much more memory demand and able to preserve finer details than voxels. And probably the latest Euclidean data type representation is multi-view. Why it's so good for representation, because when we describe three-dimensional objects from multiple by views from multiple points, we can reduce many negative effects, such like noise, incompleteness of shape description, occlusions that can be take place when we work, for example, with RGB-D images, and there may be illuminations problems when there are some reflected lights when we observe objects from particular points. And when we talk about number of views, it's still a problem. It's still a question, it is, because we have to find a balance between minimum amount of views that required for proper shape description, and on the other hand, we shouldn't take too much views to not make the system and description too complex. And this type of description is good for rigid objects without much deformations, and it's pretty compatible with DL tasks. Then applying volumetric description for these objects. And a few words about non-Euclidean data. Point clouds, that's a very basic data format. It's unstructured. It can be captured by available sensors, and on the other hand, it has a lack of structure. There are no information about that, just a list of points. Along with that, there are connectivity problems, because no information about nearest neighbors, and the surface ambiguity, because once again, there are only points in space, and we have to somehow reason about connections between these points. Meshes are more complex structured presentations, and they are made from a few key elements like vertices, edges, and faces. And basically, they altogether are polygonal data that try to approximate surface of our object, and in some way it can be understood as graph data, and in this way meshes are very similar to graphs. When we interpret vertices as nodes in graphs, and edges as well, interpret in the same way as in graphs. And to process this data, people invented multiple tricks how to work with graphs, and there are even graph neural networks that can be applied to this data, but it is not straightforward, and still require multiple tricks for that. So I will not talk too much about that. And just another view on types of data representations that can be divided into alternative categories, like raw data that are taken directly from sensors. Here we can see point clouds, RGB-D, and projections. Solids representations, those are volumetric data, voxels, and octrees. High-level structured data, those are graphs and three-dimensional descriptor. Surfaces, as I said, they are described by meshes, and multi-view is simply multi-view. So, Nothing more here. And I promised to say a few words about implicit representations. Basic idea is to try to learn some model, some neural network that will contain information about image or three-dimensional scene within the model. So one model, one set of coefficients will describe the entire scene. And when we when we feed some coordinates to this model, x, y, and for three-dimensional data z, our model outputs is values in RGB for this pixel or voxel, or it can output two values. Either this voxel is filled by the object or it is not filled. And let's view at this example. So here is a video from authors of Siren paper, and they compare three-dimensional representation of such complex three-dimensional objects by two types of activation functions, like ReLU and Siren. And they prove that their special activation function within neural networks, that is called Siren, allows better representations. So all visible pixels here are rendered only by feeding x and y z coordinates to this system, and it simply outputs either this pixel or voxel is filled with objects or not filled. And in this way, it describes the entire scene. Pretty similar approach is used in one more popular network. It is NERF. At this moment, there are more than 100 of papers dedicated to NERF similar systems, and it is as well was developed for description of three-dimensional objects and scenes, and has just another type of input data and different output. So this system it is trainable on a list of multi-view data, and when the system is trained, it output image from the new desired point of view. So first it learns three-dimensional properties of the objects, and then we can request the system to render a view of this object from previously unseen points in space. And it is done by a few complex procedures like ray tracing and rendering. And here are a few examples of how this system is working. So we have multiple rendered views, or either of such scene or a single isolated objects in the space. Here are a few examples of popular three-dimensional datasets like ShapeNet with a lot of synthetic single objects. There are PointNet datasets where objects are combined with multiple separate components, and they are all labeled. And in this way, this dataset is instance level labeled, and it is hierarchical. Another example is SceneNet for synthetic scenes of indoor synthetic indoor scenes. So it contains 5 million of photorealistic rendered images, and it was made as via three-dimensional meshes. One more data set with interior image is dataset NYU second version with RGB-D image that are additionally labeled by semantic labels. So it contains two types of data. RGB-D, as you can see on the left side, and additionally two-dimensional image was labeled for semantic labels. Regarding outdoor images, most of data sets are connected to autonomous driving, and therefore these data sets are taken on roads. And there are multiple of them, and probably most popular family of data sets for autonomous driving is Kitty. And it contain both labeled data set, for example, two-dimensional image with labeled three-dimensional boxes around objects, or data set with LiDAR point clouds labeled with some semantic labels, as you can see on this example. So we can see labels of doors, some trees, or maybe grass around around the car. And one more example, Waymo open dataset that has similar labels, but here three-dimensional boxes are labeled around point clouds from LiDAR. Okay, now let's finally go to connections of this data to deep learning. When we work with descriptors, as I said, descriptors are handcrafted features, and we extract and calculate this descriptor on the initial stage of data processing. So we've fed three-dimensional shape into a feature calculation pipeline, into some descriptor calculation model, and then use this descriptor, this feature, within some deep learning model that calculate further hierarchical features to make them more complex. And after that, we do our final work. We either predict class label or calculate some correspondence or make some semantic segmentation and so on. So basically, the process here is pretty similar to standard machine learning pipeline. When we talk about projections, the only preparation stage is actual projection into two-dimensional space. And after that, we have our standard two-dimensional image that further is processed as our conventional two-dimensional deep learning pipeline, deep learning model. When we talk about RGB-D, it is slightly more complex, but the complexity lies only in adding one additional branch for processing of depth. But the overall concept is the same. So we separately process two images, then merge their features and make final decision. With volumetric data, it is even simpler than previously. It's exactly the same as for image, but our tensors, our kernels are more complicated. For multi-view processing, it is about the same as for RGB-D data. So we have multiple separated branches for each view, then somehow merge features, and over these features calculate final prediction. And now let's take more detailed view at a few of these pipelines. So as I said, for RGB-D we have separated branches for their processing, and we can see two different backbones for original image and for depth image. They the output, they extract some features from this image, then we preprocess them and fuse into some fully connected layer as a combined descriptor of this scene. It was proven that this approach is better than we make the processing of this image together. I mean, if we combine image into 4-channel one and just add the RGB pixels plus depth value into a single image. And it turns out that such a separate branch architecture is extracts better features, extracts better knowledge than merged one. When we talk about multi-view system, approach here is exactly the same, but the difference is probably lies in the fact that all coefficients in these branches are shared, so no need to train separate branches for each view. We just train them simultaneously, and during inference simply share weights between them. When we extract features from each view, we make view pooling and extract either maximum or average value from these features, and then apply second stage convolutional neural network block to extract even more detailed finer features, and after that make our final prediction. For example, as for shape classification, we output some fully connected layer with n classes, n neurons for the final layer. When we process volumetric data, we can apply volumetric convolutional neural network, and in this case we are working with 4-dimensional kernels. Why they are 4-dimensional? Because we have a 3-dimensional kernel by itself, and along with that we have to additionally move along channel dimensions, and in this way our kernels became 4-dimensional. And for comparison, we can compare first popular neural networks for 2-dimensional data AlexNet and 3-dimensional data 3D ShapeNet. They are divided by 3 years, and for AlexNet we had input resolution 224 pixels. For 3-dimensional data we have resolution only 30 pixels in 1 dimension, and the total amount of data samples are comparable. So when we work with two-dimensional image, we can work with 200 pixels. When we work with three-dimensional data, we can use only about a few tenths of pixels because it consumes lots of memory, lots of values. And architecture is pretty similar, a few convolutional layers, one after another. And to make them smaller, they were used stride of two. And one of final parts of presentation, just a brief look at processing of point clouds. For point clouds, as they are unstructured data, we should process them regardless order of this data. And for these purposes, they were developed a PointNet. So how it looks basically? There are a few multi-layer perceptrons, a few fully connected layers that are shared for each point that we feed to our system. So as input, we have n points by 3 coordinates, x, y, z. When we calculated some more complex features, we apply max pooling to them, extract some global feature, and finally apply one more fully connected layer over this global feature to make our final prediction. When we talk about classification, we output scores for our classes. For semantic segmentation, it is more a complex one and has additional module, but I will not talk about that. So, key properties of this system. This system should be permutation or order invariant. As I said, it shouldn't be sensitive to order of points at its input. And this property is achieved by using of some symmetric functions inside the system. And as we know, these functions are not dependent on order of parameters within them. And it became quite useful to use max pooling layer. And it does its jobs for this property. So simple max pooling allows us to achieve this order invariance. And in this model, in PointNet, it is done before calculation of our global feature. And when we talk about transformation invariance, that's the second key property. It is slightly more complex task. And the basic idea is to make our input somehow standardized. So it is, shouldn't be sensitive to direction and shape of our input. And on the example on the right side, you can see the way how such transformation works. For this purpose, the special transformation, like spatial transformer, is used. It is not the same transformer as global architecture in neural networks, but it is just a specific architecture to transform input. And you can see then in this case, regardless rotation angle, output of this spatial transformer is more or less stable. with a standard position of the digit. And there are two examples for simple rotation and for synth weight spline shape description. And both these deformation models can be learned by this system. So how it is done within PointNet? This transform is applied as a special sub-module. It is called TNet in this architecture. And what it does, it calculates 3x3 transformation matrix that calculate basically it is a rotation matrix. So it allows us to rotate our three-dimensional data in a proper way. And how it is done, it is basically regression model, and it just estimates this matrix that should be applied to input data in order to make it standard rotated. And in this PointNet, such procedure is applied two times. First on initial input points and then on calculated features. And in the second case, the transformation matrix is more complex, but still the idea is the same. So we standardize our features, our rotation of data by estimation of deltas that we should apply to these inputs. And finally, just a brief view of three-dimensional data paradigms. So as with two-dimensional data, we can easily apply deep learning for understanding of three-dimensional data and make some reasoning over them, either classify them, either extract two-dimensional data, or some segmentation mask, whatever. We can apply three-dimensional representation for analysis when we try to interpret two-dimensional image using some complex intermediate representations in three dimensions, but still output it two-dimensional. And final one is three-dimensional synthesis as with images. So we have some lower dimensional data, is a text description, is an image, and output of the system is some three-dimensional object, three-dimensional shape. Further slides will be about data processing tasks and their description, but it will be not not today because too much information. Okay, thank you for your attention.